So next up, we've got Vincent. He's going to be telling us about HCG lens design.
So good afternoon. My name is Vincent Wang. I'm from Monte Vista High School in Cupertino, and I'll be talking about HCG lens design.
It's probably in the back.
Something the laser point.
Well, that's loaded. There you go.
Okay. So what does HCG stand for? Well, HCG is a high contrast gradient, which is essentially a subwavelength diffraction gradient. And it is made up in a material with a very high refractive index. So there's a high contrast between the index of the gradient bars and the index of the air surrounding air, hence the term high contrast. So in a traditional diffraction gradient, we have the uniformly spaced bars. And when we add a light source above, we get a pattern of bright and dark fringes below. But then when we reduce the spacing between the bars to less than the wavelength of the light, then we are left with only the central or the zeroth order maximum. And this results in either very high reflection or very high transmission. So in a traditional uniform HCG, it has very high reflectivity or transmission, which would make it a very good mirror. However, by slightly varying the dimensions of each bar, we can actually have an HCG that focuses the light to a point to sort of make a lens. And this has many advantages over traditional glass lens. For example, it is almost planar in shape at less than 1 micron thickness, and it has a high numerical aperture for high resolution imaging. And finally, it has monolithic integration capabilities, which like previously mentioned, we could use it in the computers to get over 100 gigahertz speed processing. So the applications of the HCG lenses include solar cells, microscopes, telescopes, and vertical cavity surface emitting lasers, or VCSELs, which are used in fiber optic communications. So this is where my project comes in. I need to design an algorithm to design the lens, and then test that lens using simulation software. So then, before I reveal the results of the simulations, let me first go briefly into the mathematical principles behind an HCG lens. So, as we mentioned previously, the lens has to be non-uniform because we want to have the light to focus. So then, in order to do that, we need to vary the phase shift from each point on the lens. So if you think of the lens as stretched out on the horizontal X position, we want the phase profile of the lens to match something like what is shown in this plot here. So then the bottom equation, phi of x, it gives the ideal lens profile for a given focal length, which is f, and a wavelength of light, which is lambda. So then in this way, we can design the phase front of the HCG to match this lens phase profile. So then the HCG will focus light to a small point. And some other design variables we need to take into consideration are the thickness of the lens, which is denoted Tg, the refractive index of the material, the period, which is the distance from the center of one bar to the center of the next bar, and the duty cycle, which is the ratio of the bar width to the period. And for my simulations, I used a refractive index of 3.48, which corresponds to the index for silicon. So now I'll go into the process that I followed to design my lens. My first step was to do some simulations in G-Solver, which solves Maxwell's equations for infinite periodic gradients. So then, using G-Solver, I first conducted a Tg lambda sweep to find a thickness that has a relatively broadband high reflectivity region. So then you can see, laser not working. Okay, no, that's not what I want to do.
Yeah, it's working.
Okay, so I chose a thickness of around 0.9 because the red here, which indicates high reflectivity, there's high reflectivity for this entire region of wavelength. So then this I thought would be a good thickness. And then my next step was to conduct a period and duty cycle sweep so that I could find the high reflectivity regions within the period and duty cycle as well to measure the bar width and the air gap for each design. And then again, we can see like the red regions around here indicate very high reflectivity, so that these are the regions that I am most interested in. So next, also using GSolver, I plotted the phase shift data for the same sweep for period and duty cycle. So then I wanted to choose a single high reflectivity region, and then within that region I needed to have a wide phase range so that I could cover every single phase value as shown on the lens phase profile previously, the one with the sort of parabolic shape. And the reason why I want to concentrate on only one high reflectivity region, for example, this kind of T shape here, is because even though each grading bar design in GSolver, when it simulates, it's infinite and periodic, which means it spreads out in all directions to infinity. But then in my actual lens, the design will only have a single bar, so that I need to keep the bar width and the air gap roughly similar so that the reflectivity and the phase shift data will still be accurate. So these are the zoomed in plots of the program I wrote to detect the high reflectivity region with a wide phase range. So then the green markers here indicate the grading bar designs that I chose for the given period and duty cycle. And then, I don't know if you can see very clearly, but these dashed lines that connect the green markers, they indicate the order in which the bars will be put into the lens. So then by connecting the dots in these figures, we will be able to construct the HCG lens. So my next step was to use the FDTD simulations, and FDTD stands for finite domain time difference, and it is a numerical method that solves Maxwell's equations. So using the algorithm I described previously, I designed lenses 100 microns wide for focal lengths of 200, 150, and 100 microns. And to the right here, we can see the intensity field profile for the 200 micron focal length lens. So then the HCG is along here at the bottom, and we have a plane wave that starts about here, hits the HCG, reflects up, and focuses to around this region over here. And the center yellow and orange red spot indicates the high intensity, which is what I want, because that indicates that the light is actually focusing. And here's the phase profile for the 150 micron lens, and also the 100 micron lens. And here's a brief movie that shows the light focusing. So again, at the bottom, here's the HCG, and we have...
When you click the laser pointer, it'll stop it.
Okay. So then at the bottom, again, the tiny gray dots is the HCG, and then their plane wave reflecting off of the lens comes up and will focus to a point about 3/4 of the way up. And now you can see it's beginning to concentrate in at one point, and now it reaches its peak intensity with the red spot, and here you can see the light starting to disperse again. So to analyze the data, I plotted the intensity cross-sections for the focal length cross-section, for each of the 3 lenses I designed. So then in this plot here, we can see, so here's the X position where the lens was, and here's the Y, which indicates intensity. And for the 100 micron focal length lens, which is shown by the blue line, it has the highest intensity peak and also the narrowest, while the 200 micron focal length lens had the widest intensity peak and the lowest as well. And this is the plot in the Z direction, so that was the vertical direction in the field profile. And then you can see here that the 100 micron lens focuses at 100, the 150 focuses at 150, and the 200 focuses at 200. So then the simulation results confirm that my design algorithm works, and the light focuses well in both the X and the Z directions. So even though HCG lenses, they have the potential to be have a very high numerical aperture for great image resolution, the lenses I designed had only a numerical aperture of around 0.447, which is not very good even when compared to a traditional glass lens. So logically, the next step in my project was trying to design a lens with a higher numerical aperture. So then for this design, I chose a focal length of 30 microns and a grading width of 80 microns because this would yield a numerical aperture of 0.8. However, even with this higher numerical aperture, the reflectivity dropped to around 60% when compared to almost 80% for the previous designs. But the plus side is that the image resolution equation shown here, R equals 0.61 times lambda over NA, where lambda is the wavelength of light, and NA is the numerical aperture. Using this lens, we can image features as small as 1 microns using a wavelength of 1.55 microns. And to the right here, we can see the intensity field profile for the high numerical aperture lens. And as you can see here, there's a lot of loss on the sides, as well as light loss that is transmitted through the gradient, not reflected. But even so, there is still a decent focusing effect that you can see. So next in my project, I decided to image the focal spot at different vertical levels to demonstrate the focusing effect. So in this setup here, we have the light source that shines down the HCG lens on a translation stage. And when the light is reflected, it is focused through a series of lenses to a charge coupled device, or CCD, which generates the image. And by moving the translation stage up and down, we can image the focal spot of the lens at different vertical positions. So this is an image of the lens taken using a scanning electron microscope. This is not the CCD image, but we can see here that the lens, this is only 2 microns, so the diameter around here is about 15 microns, and for a bit of perspective, human hairs on average can have a diameter of almost 100 microns. So then this is actually a very, very small lens here. And this is a movie that shows what we saw using the CCD. So the light begins in focus, and as we move farther or closer away, the image spot becomes wider. And we can actually see very interesting effects of like a donut shape, and then sort of like a water droplet shape. And then at the end, towards the end of the video, you can see that there are the 2 rings here, and then also the emergence of the 3rd order maximum in the middle. So to plot the experimental data, we found the full width half maximum for the length. And the reason why we chose the full width half maximum is because it's a Gaussian laser source, so which means that the intensity never reaches 0, so we needed to find a way to determine the width of the spot. So then full width half maximum is basically taking the width where the intensity is at half of its maximum value. And this is the full width half maximum plot versus the Z position. So you can see right about where it's in focus, the focus spot is very small, and as we move farther or closer away, it becomes much larger. So the next part of my project, which I personally found to be the most interesting, was the reflection dependence of the grading bars on the shape of the grading bars. So then previously we have assumed that in a diffraction grading, the bars are all perfectly rectangular, but due to manufacturing imperfections, we might end up with perhaps rough edged bars or even trapezoidal bars. And this is a close-up of what a rough edged bar might look like. So we have an extra lump here, and some concavity here. So then I plotted the intensity versus wavelength for all of these 3 scenarios. And as you can see here, the curves all have more or less the same shape, which indicates that reflectivity is not too dependent on the shape. And interestingly, the trapezoidal bars actually ended up with the highest intensity peak of 99.8%, while the uniform bars actually ended up with the lowest intensity peak of only 98%. So if I were to continue this project, I would try to design a better algorithm for a more continuous grading, because that would yield higher reflectivity. And this is especially true for the high numerical aperture lens, because I want to increase the 60% reflectivity to around 80% or even higher. And I might also want to experiment with more grading bar shapes, perhaps circles or various polygons, to see what effect that would achieve. So finally, to make some acknowledgments, I'd like to thank the VNI SHARP program directed by Professor Connie Cheng Hasnain for giving me the research opportunities. I'd like to thank my mentors, Wei Jin, Adair, Andy, and James for providing guidance along the way, and to Aaron, Evie, and Avi for coordinating the entire program. And those are some image sources, and that's it. So, Rebecca?
So in your simulation with the rough edge rectangles, how did you create that roughness?
So, you're referring to this one, right? So, along each of the 4 edges, I chose 4 random points. And then say for the left edge, at each of those random points, I would shift them either to the left or to the right by up to 10 nanometers because that is the error involved in the manufacturing. So then I used a random number generator, so then in the simulation, each gradient bar would be different. Any other questions?
One more.
Kevin?
So then if you ran the program twice, it would come out with slightly different results?
Yes, that's true. In the back? Yeah.
How did you choose the points in the fractals and phase map?
So basically, I just wanted to choose points that have high reflectivity and also closely match with the phase. So that in the parabolic plot earlier, we want to approximate that shape as closely as possible. So then I want you see here all these points are within high reflectivity, but then they also cover the entire phase range from red to blue.
For each phase, you have a lot of points you can choose.
Yes, but then I focused on I chose the point with the closest phase to where the ideal value would be.
Even for an ideal value, there are several points for that phase.
Well then, if there are several ones with the same ideal value, I just pick one of them arbitrarily.
Did you manually pick?
I used a MATLAB program.